Hello, my name is Pejcha. I'm a graduate student at The Ohio State University, and I'm here to report on a recent paper with Joe Antonini, Ben Sheppy, and Todd Thompson, which is entitled Greatly Enhanced Eccentricity Oscillations in Quadruple Systems Composed of Two Binaries. Implications for Stars, Planets, and Transients. I'd like to introduce you to some of the basic points that we make in the paper. The long-term orbital evolution of hierarchical systems of stars and planets is subject to quasi-Lidov cycles, which transfer the angular momentum between the inner and outer orbits. As a result, the inner binary can experience high eccentricity and close periastron passages. During these close passages, physical effects that would otherwise be negligible can significantly change the dynamics of the inner binary. For example, tidal friction removes orbital energy and decreases the semi-major axis of the inner binary. This can potentially explain the existence of short-period binaries and hot Jupiters. The high eccentricities can also decrease the gravitational wave merger time of compact objects. Quasi-Lidov cycles can also change the angular momentum of the inner binary in such a way that the two stars collide without any previous tidal interaction. Motivated by recent discoveries of double eclipsing binaries, we investigate the long-term orbital dynamics of hierarchical quadruple systems composed of two binaries on a mutual orbit. In these systems, each binary acts as a distant perturber, inducing quasi-Lidov cycles on the other binary. Since the perturber is not a point mass, the evolution of such quadruple systems can in principle differ from a combination of two uncoupled three-body quasi-Lidov processes. In our paper, we show that the two binaries on a mutual orbit experience very high eccentricities, orbital flips, and stellar collisions for a much bigger fraction of perimeter space than triples. Here we show time evolution of eccentricities for a quadruple system. Binary A, plotted with blue line, initially shows only small eccentricity variations, while binary B, plotted with red line, reaches high eccentricities. Suddenly, binary A flips its orbital orientation and goes through many epochs of high eccentricity. The amplitude of the cycles in binary B decreases. This behavior is completely unexpected and suggests that the quasi-Lidov cycles of the two binaries are coupled and that the perimeter space yielding high eccentricities is much bigger in quadruples than in triples. Here we show a fraction of systems that reach high eccentricity as a function of semi-major axis ratio of the two binaries. The blue and red circles connected by a line indicate results for the two binaries forming a quadruple. The triangles and diamonds connected by a line indicate results from triple systems where either binary A or B was replaced by a point mass with the same total mass. About 30 to 50% of quadruples reach high eccentricities in either binary, and this is 3 to 10 times more than for otherwise equivalent triples. Although quadruples are about 5 times less frequent than triples in the field, their lower frequency is approximately compensated for by the higher efficiency of their quasi-Lidov cycles. Quadruples are thus an order unity correction to any population synthesis results involving quasi-Lidov cycles in triples. Since quadruples might be more frequent in star-forming regions, quadruples might be a significant source of triples. Additionally, quadruple evolution can produce outcomes that would not be achieved by triples and can involve close binaries, mergers, blue stragglers, collisions, and associated transients. Stellar collisions without previous tidal interaction might be an important channel of supernovae 1a in the field. We find that such collisions are also enhanced in quadruples with respect to triples. This plot shows fraction of binaries experiencing collisions without any previous tidal interaction as a function of inclination of the two binaries. For this quadruple, 1/5 to 1/4 of binaries experience collisions, which is by a factor of 5 to 10 more than in otherwise equivalent triples. Finally, we show orbital flip fractions for star plus planet systems orbiting another binary. The lower panel shows the flip fraction as a function of the inclination of the star plus planet x-axis and the stellar binary y-axis. The upper panel shows with a black line the flip fraction integrated over all orientations of the stellar binary. The green line is for the triple system, which has the distant binary replaced by a point mass with the same total mass. The flip fraction in this quadruple is about 3 times higher than for an otherwise equivalent triple. Star-planet collisions are similarly enhanced. This has implications for properties of planets in triple star systems. If you'd like to read more about the details of our results and methods, please take a look at our paper, which was posted on the astro-ph archive today.